So there's two broad topics that we could be, I could be talking about, and presumably they'll ultimately be understanding. Presumably, they will be related to each other, but at least at the moment, they're related to different seeming kinds of a question. So one of them is just to just continue talking about this object and talking about what the residues look like for other k and n. So we finished the story with k equals 1 last time. Sorry? How to label them, exactly. How to label them, how to compute them, even compute, yeah, that's right. How to label, how to compute, how to see the relations between them, and the part that, so that's a part that, as I mentioned before, we roughly understand. I mean, we can't prove everything, but it's, and there are some subtleties as you get to high enough k and n. But we sort of roughly, we get this basic picture I've mentioned a number of times. There's this Russian doll structure, which is involved both in labeling the residues and computing them. And when I say computing them, I mean you write down a formula where there's no integral to be done. I mean, it's formally written as an integral, but there's as many integration variables as delta functions. So it's just one gigantic Jacobian. Of course, the residue itself is one gigantic Jacobian, but you have to work a lot harder. I mean, you start with many, many more variables, and then get yourself down finally to the. But we think we know at least the structure of the formula for the residue that goes along with a given labeling. Yeah. Oh, it's true. Yeah, I mean, we can have many, many solutions, you mean? No, so you mean something else?
Yes, you could, if you have something like delta x squared, delta y.
Oh, sorry. I mean, you have to, a bunch of polynomial equations you have to solve, and then a Jacobian on top of that. But
if there are multiple zero, it's not just a Jacobian. It's more complicated.
I mean, it's going to be, so we're talking about just 1, 0 in the end, right? Yeah, yeah. So yeah, you're right. I mean, yeah, I shouldn't have said just Jacobian, but the process of solving the delta functions. But it's that kind of situation where we have as many integration variables as the delta functions. Yeah. Yeah. Yeah.
Basically, the situation is that all the identities and relations that you know and think are interesting are sort of visually apparent on the polytope side.
Only in this case, in this trivial case, k equals 1 that I told you about, and we are searching for such a generalization. Yes. Yeah.
Right. I understand that.
Yeah. But that's what we want to see. This story is very algebraic. I'm not sure what you call it, but it's but you think about what the k by n matrix looks like. You think about the linear relationships between the rows, between the columns, and the label is associated with something. The label is associated with something like that, and the relations are associated with doing some simple. I mean, the relations in the labels are closely related to each other, and so on. What we'd like is a geometric picture that makes all of that much more apparent. Now we know, I mean, we found some literature about matroids and things like that, where there seems to be some. There does seem to be some way of associating polytopes with pictures in Grassmannians. This kind of this kind of Russian doll structure, specifying it goes hand in hand with specifying some kind of polytope, and then taking boundaries of that polytope is somehow. Anyway, this is all very vague. So I don't know if this sort of literature is. It was a sort of random searches that led us to this literature. I don't know if it's arcane or correct or good or bad or anything. But so this is vague, but we strongly think and hope that it exists. And I can tell you that sort of simple things that we're stuck on. Because it's quite clear that whatever these polytopes are, they somehow live in Grassmannians and not in copies of CP4. And so already just thinking about volumes in Grassmannians is more, even thinking about volumes in G24 is more challenging than thinking about them in projective spaces. It's more curvy. It's,
Before it
right.
was not really projective space, but the complement of
Yes, that's right. Yes, right. Yeah, so here it'll be the Grassmannian plus some line at for example, in G24, it would be the Grassmannian in the complement also of some particular two-plane. That it must be something like that, but we can't yet identify a nice. I can tell you the very simplest case where there's something that must be possible that we don't know how to do. I think if we just even a clue in the simplest possible case, and I think everything would start making sense.
Yes, in the case of projective space, I think it was crucial that the complement of infinity was contractible to be able to know that if something is
The inside or the outside. Oh, right.
the
Yes.
boundary of something. So, do you know what is the topology of the complement?
I think exactly. I mean, just to jump. Let me just jump ahead for a second. If we think about, and we can even simplify our life and ask questions. And well, let me just tell you a question in G24 that I can just say immediately. And if we had a good answer to this question, then we could go back and it would be very useful. So let's say you're in G24.
Your notation is linear. It's
Sorry?
linear two-space in linear form.
Yes, linear two-space and linear four space. Okay, so we know that so we can think of this as alternately as lines in CP3, and we know this is the same as points in space-time. So let me think about it instead. So let me think about the correspondence between this and Minkowski space-time. Compactified, yes, exactly. And in fact, that's going to be the point. So in this picture, that there's the line at infinity, or the two-plane. Well, there was some special two-plane. We can call it I. Okay, and this maps to the point at infinity in space-time, right? But now we can ask the following question: given four.
Wait, space-time?
Yeah. I mean, lines in CP3 are points in space-time. So we add a point at infinity to conformally compactify space-time, and we think of that as some privileged two-plane in G24 or privileged line in CP3.
G24 is a quadratic, and if you remove the tangent space at one point of this quadratic, then you get Minkowski space with the signature you want to.
Wait, so when you say remove a plane, I think of points in GP24 as a plane. You're not removing a point.
Now, I'm removing a plane. And sorry. I'm sorry, you're right. Removing a point in G24 removes a point in space. Removing a particular two-plane in 4 dimensions. A point in G24 corresponds to a point in space-time. Sorry. So a particular two-plane in G24 is an association with points in space-time.
Right.
So
G24 minus a point does not have the same topology as R3, as R4.
minus a point.
No, but the compactibility of Minkowski space is not by a point, it's by a rule.
Right, exactly. So that's exactly the point.
So,
So we add sort of, it's conformal infinity. It's all the.
So you're adding a point for every direction in the light cone or
Right.
something like that?
That ends up at infinity. Right. Right. Sorry. Yeah.
Yikes.
Yeah. Boy, that was worse than the first one. Let's see. I think I can repair it, probably. That's pretty interesting. Sorry. Yeah, that's, no, this is beyond my ability. Oh, wait, maybe do I do it like that? Do you know, is that supposed to be like that or something?
Yeah, sort of. Oh,
Okay.
there you go.
Thank you.
No problem.
So in G24 there's a particular point.
In G24, there's a particular,
plane,
right,
and you remove all the plane which
right.
it is not
Yes,
transverse.
exactly. Right. So, but now we can ask the question about defining some volume in a natural way. So, for example, let's say we have 2 points in space-time, x1.
Sorry, so here you're saying you remove a Schubert.
Yes.
Right. You
And so
remove
we have the
the
hyperspace.
hypersurface Schubert.
So you, right,
All right. And these are the affine space.
Yes.
so G24 has 6 Schubert cells, you remove 5 of them, the largest one is
Yes.
Is-
that's
is,
the
uh,
XL.
is contractible as Schubert cells are always.
Yeah, so we can remove 1, 2, xy for all xy, and then just, right. And then 1, 2 is the special. Yeah, so so imagine now we're just in real space-time, real Minkowski space-time. If I have 2 points, I mean, I'm trying to make an analog with the area of the polygons and the volumes of the polyhedra. If I have 2 points, x1 and x3, let me call it, which are time-like separated from each other, then I can look at the intersection of the future light cone of one and the past light cone of the other. Okay, and that's a nice compact region, and I can talk about the space-time volume of that region. So here are 2 points in G24. At least on this real slide, so it must be that 2 points in G24 can consistently define some inside, some volume that you can talk about. Okay. So this volume is also trivial to compute. It's x1 minus x3 squared as a 4-dimensional volume. I mean, it can only depend on x1 minus x3 squared. Yeah. Oh, I'm sorry. Pi equals 1. Yes. Sorry. Yeah. Pi equals very 1. Yes. Yeah.
By x1 minus x3 squared, you mean the quadratic form evaluated on? I mean, light.
I mean,
Light cone is defined by a quadratic equation.
Right.
And it's that.
That's the quadratic form.
Yeah. It's that quadratic form exactly. The light cone is defined by the quadratic form x mu x nu eta mu nu equals 0, where eta mu nu is minus 1 1 1 1. Okay, so it's so real light cones in Minkowski space, and so I mean, very concretely, I can take the coordinates of that to be negative t0 0, that to be t0 0 0. So just 2 things that are time-like separated. So I can just compute, I compute the volume. It's t to the 4th. It's, there's nothing else it can be. Okay.
And I would expect that if we complexify, we have 2 bounds, we have 2 corresponding quadratic cones, and we want a circle
Right,
whose boundary are the union of those, and not hitting infinity of
Right. Right.
Right.
That after all, again, just like in our polygon examples, that's what defines the difference between this and that, because these hit infinity and that one doesn't. So it's just exactly the same, right? Okay. Now, let me tell you the problem we need solved. I mean, what kind of volume we'd like to find, which we cannot seem to find any way of finding some volume interpretation in G24 that gives us this answer. Okay. So what we want is, if we have 4 points, x1, x2, x3, x4, which are mutually one null separated from the next. So this is just our picture of that polygon that we talked about many times. So imagine that x1 is null separated from x2, is null separated from x3, yeah, is null separated from x4.
So
Okay?
cyclically
Null separated.
X2 and
Right.
X4 are not.
Exactly. X1 and x3 are not, x2 and x4 are not. Okay? Okay? So what we're looking for is an answer. We want to see, is there any volume, any region, anything that would give us the answer x1 minus x3 squared, x2 minus x4 squared. That's what we desire. Is this the volume of something?
Can you show the answer?
Okay, right.
That is the question.
And right, and I can tell you the obvious things that do not work. For example, if all these, now it may well be it may well be that the and really do anything you want that you're allowed with the data. I mean everything which is Lorentz invariant, you know, anything sensible with the data. The most obvious thing is to use the light cones, you know, emanating from these points as defining boundaries somehow. If we do that, then it seems hopeless. Certainly, if we draw a real picture, if we imagine that all these points are real, then well, okay. Let's say that we take x1 and x3 to be time-like separated, just like in this picture. Okay. So then we have this light cone, we have that light cone. So x2 and x4 have got to lie somewhere on this circle. Well, it's really anyway, it's really one higher dimensional, but x2's got to be here somewhere. So let's just make it easier to visualize by putting x2 there, and x4 is somewhere else. So x2 and x4 are space-like separated. That's fine. x1 and x3 time-like. x2 and x4 space-like separated. That's fine. But the problem is that now there's simply no other region other than that one. Just because the outside of the light cone, well,
No other compact region.
exactly. There's no other compact region. There's no other compact region we can see in our face.
No other compact region which you get by taking intersections and unions and set theoretic objects of
Right.
various light codes.
Yes,
I mean,
right.
There are lots of things you can do in Grassmannians of two planes in four space.
Great. Well, let me tell you some of the other things that we've tried. But
So you
Yeah.
want something for real dimensional because
yes, it has to be for real dimensional. So it's
The degree of homogeneity.
yes,
of that.
just because of the degree of homogeneity. It's for real dimensional that returns that answer. The other things that we try, I mean, there's of course two other natural points, which are the 2 points which are the solution to the Schubert problem of the 2 points that are not separated from all 4 of these. So if we ask in general, if we're given 4 general points, to find points that are null separated from those 4 general points, then back in
This is the real Schubert.
this is the real original Mr. Schubert problem, exactly. The Mr. Schubert problem of 4 lines in P3. So we have our 4 lines in P3, and we're looking for the line that intersects all. We're looking for the 2 lines that intersect all 4. In this particular case, it's much simpler. It's even simpler. It's more degenerate because these lines one intersect the next. So it's this situation,
In fact, that's how Schubert.
right?
That was
Right.
one of Schubert's actual
Right.
ways
Of figuring it out. What was to do it that way, indeed. And so we have these 2 other special. Yeah, we have these 2 other special lines. Okay. Okay, so we do have these 2 other special lines. In general, if these points are real, those lines are complex. So there's some points often complexified in Minkowski space somewhere. So at least in this real slice, there are other natural things that you could talk about. For example, you could talk about the points that are null, the space here, which is null separated from one of those special points, right? And that's some kind of curve on this light cone that passes through all 4 of the points. but it's something that looks like that. So if I look at all the points in real space-time that are null separated from these four, that's some one lower. There's of course one more dimension, but it's a codimension 2. It's a two-dimensional region. So there's a three-dimensional region, which is the boundary of the light cone, but things that are null separated from these special points are two-dimensional. Now, if we could figure out something to do with this data to define a volume to give us this answer, we'd be very happy. But we haven't managed to do it. So anyway, this is the simplest version of our polytope problem. The very, very simplest version of our polytope problem.
That's
Yeah.
really I mean, in this degree, there aren't very many sort of.
No, it's just that. No, that's right. It's this. So this is the only one that's missing, because we can have that, we can have that, or we can have that, and that's it.
So
The one that we want is the one that we can't get.
right, there aren't very many questions.
Yes, yeah, there aren't very many questions, and we can't find that one as an answer. It's really that simple. And yet we have there are some formal Fourier transformations that you can do analogous to the ones that we did. Here I've just sort of jumped to what the sort of problem is. I could go back and lead up to why it's this question,
And you
yeah.
want to integrate products of the xi.
Sorry?
You want to integrate the obvious volume for.
Yes. Yes.
And you have no reason nothing about guessing what the boundary of this.
No. We have a formal formula that would, in principle, tell us what the boundary is if we only knew how to do this nonlinear Fourier transform. I mean, perhaps I could write it. Maybe it would be helpful if I wrote it down. But
Wait, I don't
yeah.
understand your expression. You said the boundary, you mean this four-dimensional cycle in
Yes.
complex space, the boundary of
Yes.
that.
Yes.
What is this transform?
Huh?
What is this?
Yeah. So it's well, okay. So perhaps maybe I can just. I'll also skip ahead a little bit, and I can say how we get to this question. But well, let me perhaps by way of motivating it, let me remind you that when we did this k equals 1 problem, and we could derive its polytope interpretation. We did it by Fourier representing, of course, it was all illegal, formally illegal, but we did it by formally representing this delta function. And then at some point we encountered this object, C1, and these were these bosonic W dot Z's plus C2, W dot Z2 plus C5, W dot Z5. And we're very happy because integral dc over c e to the I c x, we could quote unquote replace with step function of x, and think of this as specifying some boundary. So this specified one of the faces of the polytope. So that ultimately we had an integral over w. So ultimately we had an integral d4 w with these step functions, step function of w dot z1 up to step function of w dot z5, which we could think of as just telling us to live, specifying the faces of the polytope. Okay? So in this case, we could think of this integral as specifying a boundary in W space. Okay? Now, if we just follow exactly the same procedure, what we have to do here is, let me not erase that. Oops. If we follow exactly the same procedure, what we need to do here is the integral, it won't surprise you, d2 times 6c over 1, 2, 2, 3, 6, 1. Now, it's very important, it sounds like a trivial point, but it's very important here that there's no GL1 there anymore, right? Those are really honest. We're not setting any of the C's to 1. They're just full honest integrals over all 5 variables. So similarly here, this is really an integral over 12 variables. We're not modding out. This is not an integral over the Grassmannian G26. So sorry, this is for the, this is going to give us an answer in G26. The G24 is just a toy version of it, but anyway, the integral we need to do in general, well, okay, what we really need to do is this, is C alpha A, and then it's some W alpha dot ZA. So now before we had 1 W, now we have 2 W's. Okay? And, but now note, because everything here is GL2 invariant, whatever the answer is here can only depend on if I think of this as what I called up there X, if I now call this X alpha A, okay? This thought of as a function of X alpha A will only depend on the minors of this. So X alpha A is another 2 by 6 matrix, right? So X is some 2 by 6 matrix. But because the measure is GL2 invariant, whatever this is got to only depend on the minors of this matrix X. Okay? So this is just so f of X is really some function. So this is a function on G26, where I think of the W's as giving me the 2 rows of the G26 Grassmannian. So this is some function on that's made out of W alpha, W beta, ZA, ZB, but contracted with an epsilon symbol for the W's. So this is some function on G26. And formally, it looks like it's. Formally, it looks like it's some kind of specifying some kind of boundary, just like that one is. The sense in which it's giving a boundary up here, the sense in which you might say it's a boundary is if you hit this with differential operators on the x, you can notice that it turns into a delta function. So whatever this is, if you differentiate it, in this case, you differentiate it once, you just get a delta function. So it's some kind of step function. Similarly here, if we differentiate this thing enough with respect to the x's, and we just contract them all with the epsilons, we can just kill all the minors and be left with a delta function again. So whatever this function is, if you differentiate it often enough, you're going to get a delta function. So that it smells like it's defining some kind of boundary. It's defining some nice region. And all we need to do is integrate. So the integral over G26 of this function is what we're after. Just that. Just like here, it just ended up being that. So here we're after something like this, huh?
You have over here. Are these isomorphic problems, or?
Well, yeah, because right. So here, because nothing, 6 doesn't play. So if we went back and I did everything in the original Grassmannian formula with SL2/2 rather than SL4/4, then we'd this is the problem that we'd have, and we know the answer that we want. I mean, we know the correct answer, and the correct answer corresponds to getting this for this problem.
And how do you get that answer?
Huh?
So how do you get that?
Oh, just because we know what the we know what this here what we did is start. Yeah. No.
Compute that integral there, or?
No. We don't compute it from the integral. We don't Fourier represent the delta function. We just compute the residue on the one. So remember that.
On the residue side.
Yeah, that's right, on the residue side. So the logic is we just compute. Let me just let me show you. show you very explicitly. So we can compute our.
So what you want is that on that board on the right-hand side, you want that to have a geometric interpretation.
Yeah. So right, right. Whatever the geometric. I mean, it's some measure on the Grassmannian, right? So it's the integral of some measure on the. Now, perhaps what you're saying is when you're asking before, is it just d4x, right? And then we're just looking for a boundary. I mean, maybe it's just telling us it's not that. It is not d4x and just specifying the boundary as boundaries. Maybe it's a more interesting thing that you're integrating over the Grassmannian. But whatever it is, I mean, yeah, right.
What I'm not understanding about what you're saying, in what you described the last time, the projective space case, the thing you integrated over the cycle depended on the choice of a plane.
Right.
And that plane was determined by the external.
Right. Right.
So
the place that plane comes in here is, remember that plane came in before because we went from CP3 to CP4, and we had this Z0 reference object, which was precisely playing the role of this plane at infinity, right? Here we're going from CP3 with 2 fermionic variables to we're now adding 2 extra coordinates. So we're going from 4 vectors to 6 vectors. So we have to introduce 2. So we introduce 2 special a ZA and a ZA and a ZB, a 0010, 0001. But then everything you do is GL2 invariant. So really, it's picking out exactly what we said. It's picking out a particular 2-plane in this case 6 dimensions.
but in the case of 4,
it's a particular 2-plane in 4 dimensions.
And the way you express the thing is that, so you expressed a question about associating a number to 4 points in the Grassmannian which are related in a certain way.
Right.
Is that point one of those 4 or not?
No, that point is not one of those 4.
So,
No, that's right.
Really
That,
there are 5 points.
really, there's 5 points. One of them is at infinity. Yeah, that's right. One of them is a point to infinity. Absolutely.
And the 5th point is not related in any special
No.
way to these 4.
No.
So you have 4 in this configuration plus a random 5th.
Right.
And out of that whole shooting match, you want.
That's right. Exactly.
Oh, okay, that gives more.
And as the 5th varies, the value varies?
Sorry?
As the 5th point varies?
Yes, as a 5th point varies in principle, the value varies.
The
Yes.
value will vary, I guess, because
Yeah.
of the quadratic form.
That's right. The quadratic form depends on exactly. Yeah. Yeah. So I mean, literally, I mean, if I write it, so if we imagine integrating, yeah, it's an integral over the Grassmannian. If I label a point in the Grassmannian with, if I think of it, it's G24 or G26, it doesn't matter. But if I just write it in this way, then it's it's literally ZA, ZB, DZA, wedge DZA, ZA, ZB, DZB, wedge DZB. So that's, and we have to divide by something of weight 4 in ZA, ZB. And I do that by picking some random UV. So this is meant to be analogous to what we did before, which was W, W dW 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 in CP4 over W dot Z I called it Z naught before. I can call it ZA to the 5th. So now it's an integral over the Grassmannian. The role of ZA is played by some special point AB. Right. But somehow we know the answer that we want. So this should depend on the points 1, 2, 3, and 4 as well, such that the answer is 1, 2, 3, 4 squared over 1, 2 UV, 2, 3 UV, 3, 4 UV, 4, 1 UV. Just like this one ended up being 1, 2, 3, 4, 5 to the 4th over A 1, 2, 3, 4, A 2, 3, 4, 5 up to A 5, 1, 2, 3. Yeah, so this is the G24 example. If it's in G26, we want it to be 1, 2, 3, 4, 5, 6 to the 4th over 1, 2, 3, 4 UV up to, anyway, 6, 1, 2, 3 UV. Yeah. So this is in G24, in G26. Yeah, and whatever is defining this region, whatever the heck it is, it's. I mean, if we literally shove in the function of, if we could do that, it's all formal. But if we could do that Fourier transform, it should somehow define the region over which. I mean, you would shove that in here. That's something that has weight 0 in all of the. It has weight 0 in. Sorry. I apologize for. Using such crappily randomly varying notation. This is the WA, WB, DWA, DW. Sorry about that. Just to keep things even slightly uniform between our two exercises. Okay. So beforehand, we had an integral over just points in CP4. Now we have an integrate over 2 points in, but modulo GL2. So it's an integral over the Grassmannian. So I'm labeling them by WA and WB. And it's multiplied by some function of WA, WB, and the external points, Z, A, ZB. But these things are yeah, they're anti-symmetrized in A and B, so it's GL2 invariant. And that function is what you get by doing this funny nonlinear Fourier transform. And whatever this is something of weight 0 in, I mean, it's legitimate to integrate it because it's this already has all the correct weights, so it's a weight 0, so I can integrate it. And it's some fancy kind of theta function. I don't know exactly what it maybe it's not. So just mapping it to our previous problem, if we assume that somehow this is roughly speaking theta functions made out of putting all these various minors to 0, then we're talking about the light cones, right? Because putting WA, WB, 1, 2 to 0 is the equivalent to the statement in space-time that we're making, that we're looking at the points which are light-like separated from the point 1, 2, and so on. So that's the exercise that we did before. So perhaps, anyway, so, but whatever it is, it's something which is, so maybe it's not just D4x. Maybe there's a fancier measure. but it has to return the answer that I told you. Yeah.
So is there a reason that it must have a polytope type of interpretation, or is that just the hope?
No, that's just the hope. I mean, the reason is that yeah.
If that hope were realized, how would that help you?
Yeah, if that hope were realized, I think it would. I mean, a little more invariantly, what it means to have such an interpretation is hopefully you have some universal object or set of objects, and all the information about the external data just goes into specifying boundaries of some region of integration, so that residue theorems. So the residue theorems relations on the Grassmannian become obvious here. So that's now we know for a fact that there are relations on this side, and we also know that that when we write these physical objects like the tree amplitudes, for example, that we can write them in many different forms, and proving their equivalence needs these relations. But we still don't know how to give, I mean, even though we can verify by hand using these identities that the different forms give you the same answer, we don't know how to do that in general. I mean, if we knew how to do that, for all amplitudes, for all tree amplitudes even, we had some general argument for it, we'd be very, very happy. We don't know how to do that in general. We know it's true in every example. Yeah. You can find the residue theorems that make it possible, right? Exactly, and B, the real hope is how beautifully it worked out in the simplest case. That there you got even more. I mean, it's not just that it'll geometrize these relations between the residues. It's not just that. It's that by giving it gives the invariant definition for what the thing is, and on top of that, it tells you other ways of computing it. That was the real glory, if you like, last time. Is that we actually found a new formula, and that formula was illuminated the physics immensely because it was manifestly local, right? So it just really that there's some fascinating correspondence between, at least in that case, even though it's almost totally trivial, there is some fascinating correspondence between something that's very algebraic on this side and something that's very geometric on another side. And so it just feels like, and these formal manipulations even suggest that it should exist. This is the other reason why. This is the other reason, right?
I mean, so
right.
Here you have these, well, you call them they're like heaviside functions,
right? Right.
And but you don't have the analog of that over here. You're missing the analog of that.
Yes, well, we're missing because we don't know how to do the integral. and you see, so they don't factor, obviously. They're all connected up with each other. These little minors make it. Yeah, we don't know how to. Yeah, right. Right. Yeah, I mean, before it was the top line, and they were just, you could do them separately.
You can't do some kind of Hubbard-Stonowitz to unravel it.
Yeah, you can at the expense of introducing. Yeah, I mean, right. Right. That's right. You can do it, and still taking it all the way to the end hasn't particularly helped. Yeah. So again, perhaps this is I mean, you might be right. It might be a complete red herring. Maybe there is no polytope picture. There's which is why. But as a kind of hope for seeing more of what the picture might be, it's possible to just go back to look at these relations that we can understand just algebraically from the Grassmannian side, and see if the kinds of structures that are there have any smell, have any polytopy smell to them. Already in this k equals 1 case, we saw that it was true because the relations, even though the variables lived in CP3/4, the relations looked just like the boundary, looked just like the chopping up a polytope in CP4, right? So it told us that whatever it is, it should be associated with something living in CP4. Already from the Grass, so I mean, I don't want to say that this problem isn't our only problem. It's just the sort of simplest version of the kind of problem that we'd have to solve to find and maybe this whole Fourier transform way of thinking about it is just completely irrelevant, and really there's some more direct algebraic or geometric way of seeing where these kinds of objects come from. But we already know on the other side that the relations start being much more intricate and interesting when you get to k equals 2. So it feels a lot like something which is probably living in a much bigger space. That maybe already the objects are living not even in G26. I mean, they might be living in a much, much bigger space, oriented in different ways in this big space. The relations start being a lot more intricate already at k equals 2. So anyway, so that's something I'd be well. So this was really the question about the things that we could talk about. So one thing is to just tell you more about what we know about these relations and residues and so on.
Actually,
Yeah.
could I ask a question? So, I remember, well, I'm going to go in Moscow. I worked out. So if you have 6 points in the Grassmannian like that, each one determines a Schubert cycle, so that gives you 6 Schubert cycles. And if you look in the real Grassmannian, as I recall, that gives you 6 codimension 1. So such a point determines a codimension 1 Schubert cycle. So my recollection was that those divide it up into 24 pieces, 24 congruent pieces. Well, sorry, they're congruent if...
So you're saying if all these points are in the real Grassmannian. So if we put all these points.
I mean, of course, it has a complex picture.
Sure,
It's
right.
all algebraic. Yes,
Right.
But just to say something very, very, very concrete, those.
What do you start with?
You start with the real Grassmannian of 2 planes in 4 space and extract from it the 6 codimension 1 Schubert cycles corresponding to 6. So each point determines the codimension 1 Schubert cycle.
Yes.
For 6 lines that are in that configuration, for 6 two planes that are in that kind of configuration.
That's right.
Yeah.
And so just throw them out. What you've got left.
Do you mean in the special configuration or the general configuration with 4 general lines and
Or one. I mean,
And the other 2.
But see, there's no difference because that's L2x transitively on configurations like that.
okay, yeah.
So topologically it won't matter, but the volumes, of course, will change.
right.
But anyhow, it splits it up into, as I recall, 24 identical pieces, which have gorgeous topology. I don't know. Well, maybe it's worth looking at. But
Yeah.
you said you tried a bunch of things. I mean, this is the shape which I think is.
This not. I have not tried this. I have not. I mean, I've seen shapes like this in some of the. No, I've not. We've not looked at that. So it's those 4. I see. So perhaps there's some degeneration or something when they go to this, when everything becomes lives in real Minkowski space, which is not the real Grassmannian, of course. I mean, so somehow that's yeah. The real Grassmannian is the 2,2 signature, right? So you say in the 2,2, right?
But it's really an
No, right.
I mean,
Right.
What it means is that each one of these corresponds to a cycle in the complex algebraic situation. Sorry, a 4 cycle whose saying is, as Pierre pointed out in the discussion we had before, one of the functions of this hyperplane at infinity was picking out which one of the pieces.
Right. So, but we do the same thing. So we just add this special guy at infinity, and then compute. And I suppose one could compute the volume in exactly this way, and see what you get.
So I look at in the projective tree space at the 6 line which are the third of the diagram, and then look now at the space of line which don't hit any of them, and that decompose into 24 pieces.
And the point at infinity is supposed to pick out one of those?
And as you said, that's not really the, as you say, that's a 2-2.
No, that's fine. That's fine because we don't. I mean, because this. No, that's perfectly fine. That's really perfectly fine. I'm not worried about that.
I think there's strong suspicions that any formulas we get at the end of the day are going to be valid regardless of signature.
Yeah, I mean, really, we're looking for some natural way of finding volumes in some natural force cycles in the Grassmannian. So you're saying that's right. I think I was using the space-time picture as a crutch for imagining what it might look like, the real space-time picture, but indeed we could have been looking at it in 2-2 as well. I mean, yeah. Actually, the real might, even very vaguely from this point of view, I mean, even here to get something that looks like a step function, we had to assume that all the C's were real. It was really I mean, yeah. So perhaps to find boundaries, we really should be thinking about real. I mean, even very vaguely here, it mattered to think about the C's as real variables. So we're really doing something in RP4 there, really. So maybe doing it in the real Grassmannian makes more sense, and then sort of analytically continuing away from there.
The thing I was wondering, we have on the C12 space, we have the D module where one take O and allowing pole along all those minor equals 0. This is field to invariant. So if you take Fourier transform, it's again field to invariant. So you get a new D module and Grassmannian again.
So what Fourier, in that case, what Fourier transform are you taking?
Of D modules from C12 to its dual.
From projective for affine space to
Yes. It's
I see.
linear
So-
space.
So, just the, yeah, right, okay, yes, well, yes,
So we get a lot of Grassmannian, again, a D module.
yeah.
At least one should be able to compute characteristic variety.
Bob, I think this must give you the right answer, because somehow, I mean, what anything which knows about all 4 of the points, non-trivially must somehow, well, and furthermore, which has any reason to degenerate if x1 and x3 become null separated, or x2 and x4 become null separated, or in this picture, if all of these 4 of these points become coplanar, where all of a sudden you have an infinite number of solutions to the Schubert problem, right?
Right.
So something degenerate, I mean, so if something degenerate happens to your configuration when that happens, do you know what happens to these 24? Something bad must happen in that case.
Actually,
Yeah.
because
Yeah.
the reason I was doing it,
Yeah.
I was choosing these things to be orthogonal. Well, there's a formula for patriarchal classes that comes out of this, but anyhow. So no, I did not study what happened when they degenerated, but it should be possible.
And you also need something with a cyclic symmetry, I guess.
I think, but yeah, you're right.
But
Yeah, I mean, but the cyclic symmetry might kind of be put in if you take the formula, whatever it is, and you force it to go to the special configuration, right? So if we take a general formula and then force it to go to a configuration where one intersects the next, then and just evaluate it there, then I think everything would, as you say, the actual answers are going to depend. I mean, if we computed the cycle topologically doesn't depend on it, but if I computed this volume, the answer certainly does. So we could force it into this configuration. All I'm saying is that if furthermore something bad happens, something degenerates as it sounds like it must, because these points become ill-defined right when they become coplanar. We have an infinite number of them. We have
One
so.
of these regions becomes everything, and all the others
And hopefully they go to zero. So maybe the volume just goes to zero, and that's huh?
Well, so the 24 is 4 factorial, right? It's the permutations of the 4.
Yeah, and I should say I'm not sure about 24 versus 48 or even Grassmannian versus. I mean, all these things were coming in at the time.
It's worth noting that the four mass box, which would literally be this kind of integral, if you x regulate it, it's well.
No, but
terms and it cuts out exactly those 6 lines of the Grassmannian. So the integral seems naturally the same kind of integrals where you have all 6.
no, this is.
And so it's like a universal formula for this integral that it blows up in the appropriate places.
No, but we're not talking about dilogarithms here at all. We're just talking about the rational functions, right? So that's yeah. In fact, right. I see. Well, it sounds very promising. It sounds like it'll probably be. I mean, in fact, if it does what you say, that almost all of them. Well, hopefully, one of them becomes everything, and the rest of them become nothing. And the one that becomes everything must contain the point at infinity. So any of the other ones have got to go to zero in this limit, probably, which is what we want. So if it goes to zero, if either one, yeah, I see. All right, thanks. Well, so.